All right, so we're talking about periodic trends today. If I go back, actually, you'll see. Yeah, so periodic trends. This is still Unit 8. Feel free to visit our website at mrkubuske.wordpress.com if you want to check out any documents or any other information about not only the class but what we're talking about today. We're talking about trends. So if you think of trends, like think about this map here. It's got weather trends on it. So we're here in Indiana, and if I were to ask you a general statement about weather in Indiana in January, you would probably say that it's cold. Okay, if I asked you about July, you'd probably say that it's warm. If I asked you the same question about Los Angeles over here, you would say that it's warm pretty much all year round. Now, that's a trend that has pretty much been occurring there for thousands of years. It's not going to change anytime soon. It may change day to day, but we're talking about overall, like on the whole, okay? But if I were to ask you about Chicago, Illinois, up here, okay, so if here's Indianapolis, here's Chicago, if I were to ask you about their weather and how it was similar or dissimilar to Indianapolis, you would probably say that it's pretty similar with a few minor changes. It's just a little bit different because it's a little bit further north and it's just a little bit further west. And that has a little bit to do with the weather that occurs there, okay? The same type of trends will occur, not snowing and raining, okay? But the same trends will occur on the periodic table depending on whether you're on one side or the other. Okay, different things will happen and we can tell some things about you. So that's what we're going to be talking about with periodic trends. Again, mrkubuske.wordpress.com if you have any questions or want to get these documents that you'll be using for the notes today, okay? So let's talk about atomic size first, okay? If you've done the assignment right here about atomic radius, okay, you should have gotten a graph similar to this, okay? If you'll notice, along the top of the graph, we have all of our alkali metals, lithium, sodium, potassium, rubidium, cesium, all up there. And then on the bottom, we've got all of our noble gases. Okay, well, lithium and neon are in the same period. See period 2 here. Okay, but you'll notice lithium is much bigger in size, in atomic radius size, than neon is. Okay, so even though as I go down from lithium to sodium it gets bigger, when I go from lithium across to neon, all right, the trend is that it gets smaller. So let's talk about atomic radius. What is that? Okay, the atomic radius is 1/2 the distance between the two nuclei of two atoms of the same type if they were joined together. Okay, so this right here is our atomic radius. Think of it being like O2. Okay, so these are two oxygens. The distance between the nuclei, if I cut that in half, that's the atomic radius. It's basically saying I'm going from the middle of the nucleus out into the edge of the electron cloud. Okay. So let's talk about these trends. Okay, within groups. Now remember, groups are vertical columns. Okay, within groups, all right, as the atomic number increases, the size will also increase. So in other words, as I go from lithium to sodium to potassium, okay, the size gets bigger. This is what my graph shows me. Okay, that same trend occurs no matter where you're at on the periodic table. If I go over here to the noble gases, the same trend occurs. The arrow goes up on the graph, meaning that as I go down the table, the size increases. Now, periods, the same trend will occur, okay, but in a little different way. Let me show you what I mean. Atomic radius within periods decreases as the atomic number increases. So in other words, lithium is 3. As I go to 4, 5, 6, 7, 8, 9, 10, the size actually decreases even though the atomic number increased. And then I go back to sodium here, a big increase from neon, but then it goes down to argon, potassium down to krypton, and then rubidium down to xenon. Okay, so as I go across the table, the size gets smaller. So there you go. So in general, atomic size decreases as I go from bottom to top, and then also decreases as I go from left to right. Okay. Now, why does this occur? How do I know? Like, what's the purpose? Why shouldn't it just get bigger? If I would ask you on the first day of class which one the biggest atom is, you probably would have pointed at the bottom right of the periodic table and said number 118. Technically, that's not right. Francium is the biggest, but why? Okay. Well, the atomic number increases. When that happens, the number of protons increases. And as I go down periods, I add electron shells. Well, if I'm in one period, okay, so I'm going straight across, that's just one electron shell that we're dealing with. And each time I add an atomic number, I'm adding a proton, which means that I'm adding extra pull from the nucleus, which would be what these guys are, on the electron shell, which is what the tiger is. Okay, if I've got 3 guys on here, they may not be able to pull the tiger much more than right here. But if I had a 4th guy or a 4th proton, this electron shell is going to move closer to that fence. A 5th guy, closer. A 6th guy, even closer. So each time I add a proton, it's pulling that shell in further and further and further. And that's why as I move to the right on the periodic table, the size of the atomic radius actually gets smaller. So what are the trends for atomic size? It decreases from bottom to top, and it decreases from left to right. Okay, 3 to go. Let's talk about ionic size. Okay, remember an ion is a charged atom. Okay, so during reactions, this is pretty much just review here. Metals will lose their electrons, nonmetals will gain those electrons when those two things combine. But the transfer of these electrons has a predictable effect on the size. Cations will always be smaller than the atoms from which they come from. So in other words, Na, okay, when it loses an electron and becomes Na plus is actually smaller than Na just by itself. Say the opposite occurs for anions. Anions will get larger, okay, than the atoms than they originally were. So in other words, O2, or O minus 2, meaning oxygen with a -2 charge, will be larger than just the regular oxygen atom. And you can see here some examples of that. Here's lithium, and its normal state is at 156, but when it loses an electron, it becomes Li+. Well, now all of a sudden it's down to 60. Same thing for these other two. The opposite occurs for anions. Okay, this gains an electron. The fluorine gains an electron. It was a 62, but when you gain that electron, all of a sudden it becomes a 133. It gained size. Okay, well, why? Well, let's think about our tug of war here, our game of tug of war. Okay, on the left side we've got our protons. On the right side we've got our electrons. Now, protons are trying to pull those electrons towards the nucleus. Okay, while electrons want to stay away from the nucleus. They've got so much energy, they want to stay as far away as possible. They don't want to get pulled down. Okay, so what happens if I add an extra guy to the electron team and all of a sudden we have a charge of -1? What do you think will happen to our game of tug of war? Well, obviously, the team with more guys is going to be able to pull the rope further towards them. In other words, the atom gained size. It was right here, and it just got a little bigger. If I add another player to the team, they're going to be able to pull it out even further. Okay, so now the anions are when they're larger in charge, they're also larger in ionic radius. So in other words, I went to a -2. A -2 was bigger than a -1. A -1 was bigger than neutral. So if I was up to a -3, it would go out even further. Okay. The opposite occurs for cations. If I take someone away from the electrons team and all of a sudden I have a +1 charge, well, now they're going to be able to pull that shell even closer to the nucleus. Okay. And if I did it again, I took another guy away, I have a +2 charge, well, obviously they're going to be able to pull even further in. So for cations, the larger the charge, the smaller the radius, because those protons are able to pull that electron cloud back in towards the center. So periodic trends. So this was our graph. If you did the graphs from those earlier projects, these were basically the atomic radius size. We peaked at the alkali metals and we had our little valleys at the noble gases. Ionic radius, it peaks at the nonmetals because nonmetals, remember, increase in size, and its valleys are down in the cations. So from left to right across the period, 2 trends are visible. A gradual decrease in the size of positive ions, or the cations, that's what those red arrows will show you, followed by another decrease, okay, but this time it's of anions. So anions, but remember, increased in size from what they were originally, but after that, then they will start to decrease in size, okay? So this like follows that same pattern, -3, -2, -1, and then we go back down. Okay, so this is kind of a summary picture of what exactly we're talking about. As I move up, the size will decrease because each time I go down, remember, I'm adding an electron shell. So like this is just 1 shell, 2 shells, 3 shells, 4 shells, obviously getting even bigger and bigger. And then I have 2 arrows up at the top to show the size decreasing because remember, we'll decrease in size, but then we'll have a big jump up when I get to the anions, and then they'll begin to decrease in size because a -3 is bigger than a -2 is bigger than a -1. And there's just a quick review. Okay, last 2 topics. I'll try to hurry through these because I know I'm going a little long on time. Ionization energy, okay? What are the trends among ionization energy? Well, ionization energy is the energy required to steal an electron from an atom. So think of ionization energy like security. Like this is going to protect you. Okay, the more ionization energy you have, the more energy it's going to take someone else to steal an electron from you. We don't want them to come take it from you. So how much security are you going to put up? ADT? Are you going to put out Rottweilers and have a moat or something like that? Somebody standing guard. What's your protection? What's your security? Okay. So if I look in my first ionization energies here, okay, who is going to be the hardest to steal from? Well, if I look, it's going to be helium, neon, and argon, which all happen to be noble gases. Okay? The easiest ones to steal from will be lithium, sodium, and potassium, which all happen to be alkali metals on the very left side. So in other words, you can see the trend. I'm on the far left here. This is the far right. As I go from left to right, okay, the ionization energy will increase, meaning it's going to get harder to steal electrons. Okay, same thing's true as I drop down. But now you'll notice too, as I go down from Li to Na, that energy also went down. So as I go down, there's another trend. So the data for the noble gases would look like this. You can read that general statement here, but here's the key idea. The first ionization energy tends to decrease from top to bottom. So in other words, at the top, it's higher than it is at the bottom, and then increase from left to right. So in other words, the furthest top right is going to be this place up here where helium and fluorine and neon are. That's going to be the hardest to steal electrons from. Okay. And then you can see our summary statement of that. Ionization energy increases, so it's harder to steal at the top, and then it's harder to steal at the right. So poor cesium and francium down here, they're losing electrons left and right. Okay, they can't even hang on to them. But these guys up here at the top, they don't actually lose electrons. These guys do what? They are thieves. They're going to steal electrons. Okay, fluorine is a terrible, terrible person. He thieves all the time. Look at him go, stealing this poor guy's phone, or excuse me, his electron. Okay, see his electron there? Boom, gone. There goes fluorine with it. Okay, so electronegativity is the ability of an atom to steal electrons from another element when it's in a compound. I should probably change this to say my electrons. Okay, but here he is stealing glasses in a basket, and we'll say that basket's full of electrons there. Okay, so electronegativity, it's what is your ability to steal. Okay, so if I look at my chart here on electronegativity values, okay, in Pauling units, who is the biggest thief? Well, the highest number is going to be the biggest thief, and sure enough, there's fluorine. He's a 4.0. He's a 4.0 thief. Okay, who else is a big thief? Well, oxygen's a thief, chlorine's a thief, and nitrogen's a thief. Not to mention some of these other guys on the right side. So who isn't a thief? Well, it's these same guys we're getting stolen from. These guys that were losing electrons, okay, are the ones that aren't thieves. These guys that were keeping their electrons are the ones that are thieves. Now, if I think about this and back to chemistry terms and not on thieving terms, the reason for that is that these guys on the left side have free electrons on their outer shell. In other words, they just have like 1 or 2 electrons on their outer shell that they want to get rid of because then they have that full outer shell, that octet rule. These guys on the other side, they want to steal that 1 or 2 extra electrons to fill their outer shell so they feel full, and then they feel full, feel that sense of having their outer shell filled in. So that's why the guys on the right are thieves and the guys on the left are getting their electrons stolen. They almost want them to be stolen from them. So as a general statement, electronegativity values decrease from top to bottom within a group. Okay, you can see that here. Okay, 1.0 to 0.9 to 0.8 and so on. And then they increase as they go from left to right, 1.0, 1.5 all the way to 4.0. Okay, and then there's what that periodic table would look like again. And then there's that same statement. Now, here's a quick summary. Okay, anytime I'm dealing with radius, in other words, size. Okay, radius, size, radius, size. Okay, the rule is the same. It decreases as it goes up, and it decreases as it goes to the right. So in other words, the smallest ones are going to be up here. The biggest one is going to be down here, okay, because the size decreases. Actually, the size would be smallest here. And then when it comes to electronegativity or ionization energy, which are both measures of energy in stealing electrons, okay, they're both going to increase going up, and they're both going to increase going to the right, okay. This is a great summary tool for you, okay. Now, I know we went through this kind of fast, and it can get a little confusing, but just remember this key, okay. All I'm going to be asking you is about whether they're next to each other, okay? Like for these two, let's say I'm talking about these two. Which one is going to be smaller? Which one is going to be the smaller of the two? Well, it's going to be this one based on this trend right here. Okay, what about these two on top of one another? Which one's going to be smaller? Well, it's going to be this one on top because the rule is that it increases going down and it decreases going up. That's all I'm going to ask. I'm going to ask about ones that are above and ones that are to the side. Okay, you just need to know these rules about increasing or decreasing, and then that'll help you when it comes to taking your test. All right, my 15 minutes of fame are up. I'm off. I hope you learned something. Hope this helped. I'll see